this video we look at how to distinguish between some of the different probability distributions. So we'll just start with a recap of the different distributions that we've talked about. So there was a uniform distribution. With a uniform distribution, all outcomes are equally likely. So an example would be rolling a 6-sided die. The probability of getting a 1 is 1/6, the probability of getting a 2 is 1/6, and so on. We can make a distribution table to show all of the probabilities and calculate the expected value by doing the sum of all of the x values of our random variable, so the elements of our random variable, times the probability of those happening. We figure that out for each individual item, sum them all up, and that will give us the expected value. Second, we looked at a binomial distribution. Now, with a binomial distribution, we were talking about Bernoulli trials. Those are trials that are independent and identical. And we talk about outcomes as either being successes or failures. We use the equation over here. The probability of x happening is n choose r times p to the r and q to the n minus r. Now, in this situation, n was the total number of outcomes. And r was the number of desirable outcomes. So this is the desirable outcomes. P is the probability of a success. So if we're looking for, the number of whatever it is that we're looking for, that's going to be our success. So P was considered the probability of success. The important thing to note here is that this r, the exponent here, is the number of successes. So we take the probability of success and multiply it by itself for however many successes we want to have. Q is the probability of failure. And if we had n trials, then r of them were successful, then n minus r of them are not successful. Now, for hypergeometric distribution, the trials are dependent, so there's no replacement, no repetition. And again, the outcomes are classed either as failures or successes. The equation looks like this. P at x equals a choose x. So again, a is the total number of successes. And x in this case is the number of desired number of successes, desired number of successes. B in this case is the number of failures. And if there were n trials, then n minus x has to be the number of failures that we're going to choose. A plus b is the total number of outcomes. And n is the number that are being chosen. So let's look at a couple of examples and try to decide which type of distribution to use. So here we have an example, and a study reports that 5% of adults are afraid to be home alone at night. If 20 people are randomly selected, calculate the probability that one person is afraid to be alone at night. So we're going to have one person. We want to know what the chance is that that one person is afraid to be at home alone. So in this case, we have trials. These trials are independent. If one person is afraid to be at home at night, that doesn't affect another person, another stranger, who may or may not be afraid to be home alone at night. So because these trials are independent, this is a situation where we're talking about a binomial distribution. So this is a binomial distribution because of those independent trials. So the question here asks, what's the probability that one person is afraid? Well, in this case, with a binomial distribution, we need to know what the probability of success is. So the probability of success, in this case, a success is being afraid. That's 5%, which we can write as 0.05. So if there's 5% are afraid, that means that 95% must not be afraid. So the probability of failure here has to be 0.95. So the probability of one person being afraid, so probability of one person being afraid is equal to the total number of people, n. I should maybe list that over here. N is 20. And r is the number that we want to be afraid, which is just 1. So here we end up with 20 choose 1 times the probability of success, which is 0.05, to the exponent of the number of successes that we have times 0.95 to the number of failures that we have. So the failures are all the people that are not afraid to be home alone, so that must be 19. So we can plug that into the calculator, and when we do that, we should get an answer of somewhere around 0.3774. So that means there's a 38% chance, say, that someone is afraid to be home alone at night. Okay, so moving on then to a slightly more challenging question. Here are the questions asking, what's the probability that at least 3 of them are afraid? So we want to find the probability that x is greater than or equal to 3. So at least 3 of them means that x is greater than or equal to 3. Well, that means that we're looking for the probability that x is 3 plus the probability that x is 4 plus the probability that x is 5, all the way up to the probability that x is 20. That's a lot of calculations. This would be a perfect example of when to use the indirect method. So if we're going to use the indirect method, we say that we want to find the probability, this is going to equal 1 minus the probability that x is less than 3, which is the same as 1 minus the probability that x is 0 minus the probability that x is 1 minus the probability that x is 2. And again, in order to calculate each of these probabilities, we just use the binomial distribution. We'll set it up here. So we'll have 1 minus, we still have 20 people, we want 0 of them, so this is for this part here. We want 0 of them to be afraid of being home alone, times the probability. You could probably leave this out, but I'm going to put it in just for clarity, to the 0 times the probability of failure. If there are no successes, then there must be 20 failures. And then we repeat this for one probability of one person being afraid, so it's 20 choose 1. We have 1 success, so 0.05 to the 1, and 0.95 now to the 19. So that's 1, and then we do 2 times 0.05 squared. Sorry, that's a 2. And 0.95 to the 18 now, because if there were 2 successes, there must be 18 failures. And you can plug that all into your calculator. I would probably do it in steps, but just to save us a little bit of time. So the answer here would be 1 minus whatever each of these things works out to be. And I think the answer here works out to 0.0754. So about an 8% chance that at least 3 of them will be afraid to be home alone at night. Now, in order to find the expected value for a binomial distribution, the expected value is just equal to n times p. So the number of trials, which is 20, times the probability of success. In our case, the success was being afraid to be at home alone, which is 5%. And we multiply that out, and we get a value of 1. So in this case, the expected value over the long term, if we did this repeated experiment with 20 people over and over and over again, we would expect one person to be afraid to be at home alone. Alright, let's move on to a slightly different example here. So in this case, we're drawing 5 cards from a deck of cards, and we want to know the probability of getting 3 or more hearts. So we're going to draw a card. We're not replacing it back into the deck. So in this case, these are trials that are dependent. So this is a situation where we're using a hypergeometric distribution. So this is a hypergeometric. And we want to know the probability of getting 3 or more hearts. So what really that's asking is, what is the probability that x is greater than or equal to 3? Well, the probability of getting 3 or more hearts is just equal to the probability that we get 3 hearts plus the probability that we get 4 hearts plus the probability that we get 5 hearts. We stop at 5 because this is a 5 card hand. We can't have any more than 5 hearts in a 5 card hand. Alright, let's continue on here. What is the probability that we get 3 hearts? Well, there are 13 hearts in total. We want to choose 3 of them. Sorry, that's a really bad looking 3. Let me clean that up. So we want to get 3 hearts, which means that the other 2 cards in our 5 card hand have to come from the cards that are not hearts. There are 52 cards in the deck. 13 of them are hearts, so we want to subtract 13 from 52, and we get a total of 39. So there are 39 cards that aren't hearts, and we need 2 of them. This is all out of the total number of ways that we can draw a 5 card hand. So 52 cards in the deck, and we want 5 of those cards. So it looks sort of like that. So this is just for 3, so this kind of matches up with here, and then we need to do probability of getting 4. So we just repeat the process. 13 hearts, we want 4 of them, which means that from the 39 cards that are left, we need to take 1 to round out our 5 card hand, and that's out of 52, choose 5. And then lastly, probability of getting 5 hearts. Well, there are 13 hearts. We want 5 of them. I'll put this in here. You don't need to put it in, but that means that from the rest of the 39 cards, we need 0 of them. 39, choose 0 is just 1. And that's out of 52, choose 5. Again, you can go ahead and calculate each of these, add them up, and if we've done this correctly, we should get a total of 0.09. So the probability of getting 3 or more hearts is equal to approximately 9%. In order to find, in order to find the expected number of hearts, if this is a hypergeometric distribution, the expected value here is just equal to, again, the number of trials times the probability of getting a success. So, something happened there. Let's fix that up. So times the probability of getting a success. Probability of success. So our success in this case is getting a heart. So the probability of getting a heart is 13 out of 52. And n in this case is the number of trials. Well, we're doing 5 trials. So we are multiplying by 5. We're drawing 5 cards. So if we simplify that, that works out to 65 out of 52. And we can see that that is equal to about approximately 1.25. So on average, we would expect 1.25 hearts when we get a 5 card hand. Now, obviously, you can't get a quarter of a heart in your hand, but again, this is a long-term average. If we were to do this experiment over and over again, we would expect that the average number of hearts is 1.25. So we've done a binomial distribution, we've done a hypergeometric distribution. I want to talk now about how do we tell the difference between the two. I think in these two examples it was fairly easy to see. Hypergeometric distribution, we're often drawing a certain number of items that we want and a certain number of items that we don't want, so that without replacement. And again, the trials are dependent for hypergeometric. I want to show you two examples that are very, very similar, and if you don't read them carefully, could lead to some trouble. So the first example here is that you buy 20 sausages from a store. 20 sausages from a store. We assume that 20% of them contain meat. That's the wrong way to spell meat. Meat should look more like that. So 20% of them contain meat that is not advertised on the label. Question is, what is the probability of 3 sausages having meat that is not advertised? I'll let you kind of think about this question for a second and just try to digest what it's saying. And then I want you to think about this second question. Very similar question, but slightly different. Here's the second one. In a study of 100 sausages, 20 were found to have meat that was not advertised. Out of the 100 sausages from the study, 20 are sampled. So they sample 20 of them. And the question here is asking, what is the probability that 3 of the sausages that are sampled have meat that's not advertised? These questions look almost identical. There's one key difference here that's important. In this case, we're sampling from 100 sausages. We know that there are 20 successes and 80 failures. So this is an example of a hypergeometric distribution. We're going to choose some successes. We're going to choose 3 from 20. And then, because we sampled 20 in total, we need to sample another 17. Sorry. Let's fix that up. Sorry about that. Hang on just a second here. Fix that up entirely. So we have 20, choose 3 sausages that are going to be defective. There were 100 sausages in total, and that's one of the big differences with this question. There was no total given in the question above. There is no total number of sausages. So here we know that there are 100 sausages. We need to have 80. We have 80 left that are not sort of defective, I guess. They don't have the sort of meat that's not advertised, and we want 17 of them to round out our 20 sausages. And this is all out of the total number of sausages. Choose 20. So you can see here why this one works out to a hypergeometric as opposed to a binomial. Let's have a quick peek at the one up top here. So here we know that 20% of the sausages contain meat that's not advertised, so 20% is 0.2. That's our probability of success, which means that our probability of failure is 0.8. And in this case, we're hoping for 3 successes. So R is going to equal 3. So the probability of having 3 successes is equal to sorry, I'm just trying to look for the number of sausages. 20 sausages here. So we need 20 choose 3 times the probability of success, which is 0.2, to the number of successes times the probability of failure to the number of failures. So if 3 sausages are successes, the other 17 must be failures. So you can see that these two questions very, very similar. Very minor difference, which changes how you do the question. And it turns out that actually both answers here are very similar. They're not off by a whole lot, but it is important to recognize the difference between the hypergeometric example and the binomial example. So spend some time reading through those questions carefully, maybe trying them out and seeing what the difference is, and I think that'll help a little bit.